Morning, everybody. Welcome back. I won't ask if you missed me, but I did miss you. How was Thanksgiving? Or should I say, how's the break? Because I know not all of us celebrate Thanksgiving. Things okay? Yeah. Sometimes they're good, sometimes they're bad. Depends on your individual situation, all that sort of stuff. I spent mine in a lot of pain, my back and my neck, decided to not like me again. And so it was a very stiff Thanksgiving, right? A lot of doing that. So still pretty stiff and sore, but my advice is don't roll. That's not a threat, by the way, it's just a test. Let's see here. I posted an announcement this morning. I think had everything you need to know about the last week of class here. So people are turning in their quiz sheets. That's great. Give those to me afterwards if you want. The instructions have been scrolling up on the screen. Again, just kind of key thing there. I need your name and I need the total number of points you got on quizzes. Don't tell me what it's out of, all that sort of stuff. I'll figure that out this week and I'll start getting your quiz scores into the computer. Once your score gets recorded in the computer, they'll probably start doing that tomorrow. Then it's like kind of the most accurate it will be. The one problem will be chapter 14 homework, which is due this Wednesday. After that, your grade will be the most accurate. At that point, all I've got to do is put the score in for exam 4. We're going to be taking that exam, review on Wednesday, exam on Thursday, and then the test autopsy will be when we are supposed to be taking a quote-unquote final in this class. So for finals week, you've been here, you've had other classes here, hopefully, right? Finals week, there's no regular classes at all, right? You only come to the time that we're scheduled to come, which for us, I believe, is Monday at 8 a.m. So Monday of finals week. You come in, you do the test autopsy, I update your score, and that's your grade for the semester. Right? That's it. There's no other weighting, any of that kind of stuff. And if you need to talk to me about your grade, then the test autopsy is a great time to be doing that. So we'll just be in here for a couple hours, and you'll work out your problems like you always do on the test autopsy, and then that'll be it. Any questions about this sort of last little hurrah that we have? Right. Remember, if you need to talk to me about your grade, about anything, make sure you talk to me before or on that Monday, right? That we're doing the test autopsy. We need to schedule something. We can schedule something for Tuesday or Wednesday, but I generally get all of my grades in on Wednesday of finals week. Post at the campus, and then it takes it takes admissions directors a couple weeks to figure out what they're doing, but they'll be official in 3 months. More or less, once you get your exam autopsy, you'll know your grade. I think I might have them graded by Friday. So you're taking it on Thursday, I might have graded. You want me to post the grade? Yes. Kind of a stupid question, but usually the answer is yes, Mr. Bailey. All right, for those of you who are just coming in, I'm going to take this down, or at least cover it up. It'll pop up every once in a while. But I'll put the instructions back up at the end for turning in your quiz sheets. All right. I wanted to, get the cobwebs out and get a little bit of rust off from this break by doing a couple more examples having to do with fluid dynamics, Bernoulli's equation, equation of continuity, that sort of thing. So we'll warm up on building, and then we'll move into a slightly more complicated one. And then we'll go over chapter 14 homework today. So this is a picture of the World Financial Center in Shanghai, China. And as you can see, they put a hole in it, right? And the architects probably thought it was really cool, and the engineers were sweating bullets, right? Because one of the things that happens around high-rise buildings is wind. And when you take air that's moving and it's got a lot of space to move, and then you force that air to go through a narrow street between skyscrapers or through a hole, right, in that skyscraper, what does the air have to do? If the cross-sectional area is getting smaller, what does the wind have to do? It's got to speed up. It's called the Venturi effect, but it's a consequence of Bernoulli's equation, and the air going through that hole, or even just going around the building, okay, is going to be squeezed into smaller spaces and is going to have to speed up. In the example I've got here, what we're going to do is we're going to calculate the pressure difference on a window where inside the building the air isn't moving, quote unquote. It's fairly static. Yes, there's air flow, but it tends to be slow enough that we just consider it to be atmospheric pressure. Versus the air outside the building, which in this case is moving at 11.2 meters per second, which is roughly like 25 miles an hour, something like that. Just so you're aware, in places that do have skyscrapers, like Manhattan, New York City, where the skyscrapers are only a street apart and they're fairly tall, if they get a storm and the storm's blowing, wind at 30, 40, 50 miles an hour, it's very easy for the air to, when it gets forced into those city streets between the skyscrapers, start blowing at 75 to 100 miles an hour. And that's hurricane force winds. And that's just because the air, right, went from a lot of space to move and is getting squeezed in between those skyscrapers. And the equation of continuity demands that it speeds up. Otherwise, buildings start blowing down. And in hurricanes, a lot of the damage comes from the pressure difference between the fast-moving air. So in a hurricane, you got 150, 170 mile an hour winds coming through. You've got air inside of, say, a house that's not moving, it's static. And then you've got all of this air flowing over the top of the roof at 170 miles an hour. Well, where's the low pressure? It's above the roof. It's where the fast-moving fluid is. Remember Bernoulli's principle? And so roofs will just pop off. So a lot of the destruction comes from the fluid dynamics of the moving air. Yes, there are things being blown around in a hurricane, but a lot of it comes from water damage, from the tidal surge, and then from the wind damage and the pressure differences inside and out. If you ever have a chance to look at video or photographs of after hurricane damage, look at the buildings. Look at especially like hotels and taller buildings. You will see that the windows are blown out. The glass has been pushed outwards, and like furniture and curtains and things look like they've been sucked out of the building. So you can see the evidence of Bernoulli's principle and the fluid dynamics at hand there. All right, let's do this problem. Okay, and I'm gonna just kind of draw. So like we got it's sort of like a cross section of the building here. I'm drawing the window. This is like edge on, so I've drawn it kind of thick, right? So what we've got here, this is the outside, and this is the inside of the building, and just to make sure we understand, the people are on the inside of the building, and then we have this outside, and the wind's blowing sort of across this building, and we need to calculate the pressure difference on it. So I'm going to choose 2 points. I'm going to choose inside the building, and then I'm going to choose immediately outside the building. I'm going to keep those 2 points at the same height to make my math just a little bit easier. And then I am going to employ, Bernoulli's equation with 1s and 2s on it. GH2. Okay, so again, we're looking for the pressure difference inside to outside. And are there some things that I can either just say are 0 or cancel out because they're the same on both sides? Rho GH is the same on either side, isn't it? Talking about air, we're on the same planet, and the height, right? I set both of them to 0 or at least the same height, and so they will go ahead and cancel each other out. That leaves me with pressure. Well, it's all pressure terms, but I've got these 1/2 rho v squared terms. I'm going to get all those on one side, and I'm going to get all the pressures on the other. So we're going to do P1 minus P2. Remember, I was asking for the pressure difference inside to outside. Oh, no. We want to find the force. Okay. Sorry, I jumped ahead. pressure is force divided by area, right? So if we know what pressure is acting on the window, we can solve for the force acting on the window by taking the pressure and multiplying by the area. So this pressure difference that I'm finding here, okay, is going to be the pressure on the window. And it's going to be caused by the difference between the speeds that this is going at. So what's something we can say about the speed inside the building, the speed at point 1? Like what's the wind velocity in this room right now? Good job. You're starting to think a little bit more like physicists, right? You're like, it's moving. Like you can hear the air handler fan going, right? You can hear that, right? So it's pushing air through this building, and with our new COVID protocols, we have to have a minimum amount of air exchange inside the building at all times. But compared to, say, a windy day outside, it's effectively zero, isn't it? So we'll go ahead and say that this velocity right here is 0, because it's inside the building, which means that our pressure difference over here is really going to be caused by the speed that the wind is moving. Okay? So we're going to take 1/2. We're going to multiply by the density of air, which I completely failed to write down in my notes here. I think I got it wrong or something on a different slide before. I don't remember. At any rate, density of air times this speed, 11.2 meters per second. And what I discovered, okay, is that there was a pressure difference here of 81.5 pascals. So again, I got this P1 minus P2, the pressure inside minus pressure on it. What is the pressure at point 1? It's atmospheric pressure, right? So we could go ahead and put in P naught there, okay, the 1.01 times 10 to the 5. But what I really need is this pressure difference between inside and outside, and that pressure difference is being caused by the motion of that air. I really don't want to solve for P2. I mean, I could find the pressure outside. It's 81.5. Well, it's atmospheric pressure minus 81.5. I could solve directly for P1. Again, but the problem is that the force that's on this window, right, is, if the air weren't blowing, if the wind weren't moving outside the window, what would be the net force on the window? It would be 0. But what would the pressure inside the building be? Atmospheric. What would the pressure outside the building be? Atmospheric. And vacuum, we're on the moon. It's awesome, right? Pressure is the same on either side of the window. The net force on the window is 0. What we're trying to find is what's the excess force caused by the motion of this air around the building. And so I'm not going directly for P1 or P2. I'm going for the difference between them. I want the pressure difference. And that pressure difference turns out to be 81.5 pascals. So that 81.5 pascals, that net pressure acting towards the outside, is going to, I come up with a positive pressure difference because it's going from 1 to 2. That's going to be the thing that's going to be generating force on my window. So now when I go to calculate the force on my window, I'm going to use this pressure difference times the area. I'm going to use the 81.5 pascals. And I'm going to multiply it by the area of the window. And they gave me the dimensions of the window, so that's 4 meters times 1.5 meters to get that area. And when I do that, I find that the force was 1,960 newtons towards the outside. I know it's outside because that's where the fast-moving fluid is. So roughly 2,000 newtons. And there's about 1/4 of a pound per newton. So we're talking somewhere in the neighborhood of like 225 to 250 pounds of force that's acting on this window. in this skyscraper. And talking to engineers, civil engineers that work on buildings of this nature, it's not uncommon for them to plan to have 5 to 750 pounds of excess force on these exterior windows. I'm like, holy cow, like, are you like factoring in like hurricanes and stuff? And they're like, well, yeah, but we're also factoring in idiots. People that come up and push on the windows for whatever reason. Also, a lot of buildings, including our own, don't have atmospheric pressure in them. They actually have what we call positive pressure in them, meaning that the pressure inside the building is higher than the pressure outside the building, because we want air to be pulled kind of into the intakes of the building, pressurized, and then that pushes air out of all the leaks. So when somebody opens a door, okay, you walk into a building that's positively pressured, you pull, and you'll feel the air sort of pulling in. A lot of hospitals are positive pressure, but then they also have rooms inside there that are called negative pressure rooms, where the air is coming from the outside into that room. So it just depends on the thing. But most everyday buildings, including your home, okay, if you're running the heater or the air conditioner, is going to be slightly positively pressured to make sure the airflow is out through all of the leaks. So engineers will take into account all of these factors: excess pressure from ventilation, also winds around the building, and stupid people that come up and push on them. I saw a picture, I was looking for pictures today for a building, and there's a building in New York somewhere, I think, maybe, London, one of those two, where they designed the windows to be tilted at like a 30-degree angle so that people could walk up to them and lay on the window and be looking into space.
Space Needle has that one too.
Space Needle has it. It's like different places are doing this now, right? So hopefully they designed those ones to hold up, human weight. They did the cosine of the angle. Oh, and then there's that place in the Grand Canyon. Native American tribe set up that tourist destination where there's it's a glass walkway. Everything's glass. The railing's transparent glass. The walkway is transparent glass, so you can walk out over the Grand Canyon. I have vertigo, so I think I would stay away, but I'm also a climber, so mountain climber who has vertigo. Not a good mix, but it's fun anyway. Okay, so let's do something. This one's actually pretty close to a homework problem I think I gave you. And is, well, it's not quite a siphon, but you'd be surprised how many of these kinds of systems are out there in our infrastructure. What we've got, okay, is some sort of water storage tank facility, something, okay? And there's a little tiny, there's an outlet, okay? A hose, right, that comes out of this thing. And they give us sort of the radius where it's attached towards the bottom. And you can picture this, you could do that, you could say, well, maybe the hose, it doesn't really matter, okay? Maybe the hose comes out like that, okay? And then key part here is at the end of this hose, there's like this stopper that's been placed, shoved into the end of it, so that if we sort of blow up this picture, make it look a little bit bigger, we've got the end of the hose, and then we've got this stopper, right? It's jammed in. I'm not drawing it very well, okay? It's jammed into the end of the hose here, right? And it's holding back all of that fluid. So they want us to calculate a lot of things, okay? They've told us several things, like we've got some fluid in here, and they've told us that this vertical height is 7.05 meters. They've also given us some radii to work with. So, calculate the frictional force required to keep the stopper in place. So let's talk about, so we're talking force now, right? So as soon as you hear force, what sort of toolbox or paradigm do you want to get your brain into? What laws are involved when we're dealing with forces? Oh, Newton's laws, right? Okay? So, your brain should snap towards, okay, I'm dealing with the force, free body diagrams, Newton's third law, second law, first law, right? There's all of these things going on. So, what we really want to do is kind of draw a free body diagram of the stopper. I'm just going to do it on my blown up thing. So what's pushing or pulling on the stopper? Well, there's the water trying to push it out, right? So I'm just going to draw like this force due to the water. Now we would of course we would want to think about this since it's fluid. We want to think about this in terms of pressure. There's like a pressure behind that stopper. But since they gave us the areas, we can talk about the force. There's force from that water trying to push it out. Okay. Any other objects that are pushing or pulling on that stopper? Okay, there's the friction, right, that they're asking us to solve for. So what kind of friction is it? Static friction. Good. See, you guys know a lot of stuff. That's good. So we got static friction acting on the stopper. And what direction is static friction acting? Your choices are right and left. To the left, it's trying to counter the force of the water trying to push the stopper out, right? So it's going to be acting to the left. Are there any other objects that are pushing or pulling on this stopper? There is one more, and it's easy to forget because it's the fluid nobody ever thinks about. The air on the other side of the stopper, right? Okay. There's air pressure outside of that stopper. And compared to the water, it's not very strong, right? But it is there. So we got to remember that we do have atmospheric pressure out here, and that's going to cause a force, right? We'll just call it force due to air pressure, okay? Acting on the inside. We got to take that into account. It's helping the friction, right? Without the friction, the water would win. It would overcome the force of the air pushing on that side. But it is helping a little bit, so we got to keep it in our analysis. All right. So we want this friction force, and when we add all of these forces up, do we want the acceleration of the stopper to be? We want this to be a static situation, okay? So that means we add up all of these forces, and should we call to the right positive? Does that feel good? Okay. So force of the water minus the force of the stopper minus the force of the air, right? Capital F there because it's not a friction. Okay. So if we're going to find, right, the frictional force on this stopper, we're going to have to take the frictional force of the water, or we're going to take the force of the water and have to subtract off the force of the air pressure on it. Okay, so that's our goal. We need to find the force that the water is pushing on this stopper, and then the force that the air pushing. Let's tackle the air first. It tends to be the easiest. How are we going to find the force that air pressure is exerting on that stopper?
Force over area.
Close. Pressure is force over area. So what is the force? Pressure times area, right? So in the case of the air, it's going to be atmospheric pressure times the area we have down there, the area of the stopper, right? So in a very similar vein, we're going to find the force of the water by finding the pressure that the water is exerting on that stopper times the area of that stopper, right? So I'm just kind of putting pieces together down here at the bottom and trying to figure out what it is I'm going to do. Okay, so we know atmospheric pressure and we know the area of the stopper, right? Did they tell us? Yeah, the nozzle has a radius of 1.1 centimeters. So how are we going to find the area? Pi r squared. It's a circle. Did they tell us it was a circle? No, but nobody makes square holes, right? Okay, and they gave us a radius, right? So if it was an elliptical shaped hole, they would have to give us 2. All right, so we'll assume it's a circular cross section. We know our area. We got the atmospheric pressure. We just need the pressure from the water. How are we going to find the pressure behind that stopper? We could go to Bernoulli's equation, okay, and that would work. A lot of stuff would cancel out except for one thing, which would be the rho GH term. So that's fine. You could also go straight back to the very beginning of chapter 14. The pressure anywhere in a fluid depends only on what? The height. The atmospheric pressure above it, right? Okay? And then the height of the water column. So, either way, I'll just show you that Bernoulli's equation works. We got rho V1 squared plus rho GH1 equals 2 plus 1 half rho V2 squared plus rho GH2. If we set the height to be 0 right at the end of the stopper right there, then let's see, H2 is 0, it's not moving down there. P2 is what we're looking for. H1 is not 0, it's 7.5 meters. The surface of the water, this is my point 1, I wasn't really clear there, okay? The surface of my water isn't moving, and I got atmospheric pressure, right? So I end up with a statement that says the pressure where I want to find it is going to be equal to atmospheric pressure plus rho GH. And isn't that what we had at the very beginning of chapter 14? Okay. So we can calculate that pressure. Let's see, did I do any numbers in this example? Looks like I got some numbers. Looks like I just put all my numbers in at the end because I went directly for the force on the stopper. So the force on the stopper, frictional force, is going to be the force from the water, which is the pressure from the water times the area minus the atmospheric pressure times the area. I factored out that area, pressure water minus atmospheric pressure, and then I insert this thing in for pressure water. And what happens to the two atmospheric pressures? Yeah, they cancel each other out. Pressure water is rho naught plus rho GH minus atmospheric pressure. Those go away, so I just need to take rho GH times my area, and that's when I put in all my numbers and found out that this was 27.9. So pressure and force are related to each other, right? And they're related through this idea, right, that pressure is force divided by area as kind of our definition for pressure. And so if we can figure out pressures, we can figure out the forces that are acting on them as long as we know about cross-sectional area. So, okay, we calculated that force. That was a mean combination of chapters 12 and 14. Right? Oh, but there's no ladder here, right? What else do they want to know? The stopper is removed. Okay, I suppose that's their privilege to do that. What mass of water flows out of the tank in 2 hours? Oh, so now they want to know total amount of fluid. Interesting. We remove the stopper, water begins to flow. If we're going to find out how much fluid is flowing out of this tank, we need to know how fast the water is flowing out of the tank, don't we? So now we've got to figure out how fast is the water going down there at that nozzle. I've done this problem last week. You should already know the answer. Square root of 2gh. I'll prove it to you again, but our answer is going to be the square root of 2gh. So let me clear. Whoa, no, come back. Clear that off. And let let's not clear everything off here. Let's come on. Here we go. Didn't want to come up with my selector. Let's copy that over here. Back to this point. All right, so we got this tank, and we're going to find out how fast it is. So again, points 1 and 2. Only this time, the stopper is gone, right? And the water is flowing out. My point number 2 is going to be outside where it's flowing out. So again, Bernoulli's equation, rho v1 squared plus rho gh1 equals. Same thing with 2's on it. Okay, height 2 is at 0, so that goes away. V2 is what we're looking for. Pressure 2 is atmospheric pressure, the same as pressure 1. So I can cross those out because they're the same on both sides. It said it's a big tank, so if we assume V1 is pretty much 0, then we can wipe that term out, and we know height 1 right there. So what have I got? I've got rho gh equals 1/2 rho v squared, and if I cancel out my rows and I multiply my 2's and I do some square root magic, I've got my speed. So really, as long as your tank is big and the fluid level is large and the surface of that fluid is not moving with any appreciable speed, you got it. If not, you just, instead of writing 0 for that term, you get 1/2 rho v1 squared. Well, you'll just end up with having to subtract off of v1 squared. Not the big deal. Okay, but they don't want to. We need the speed because they want to know how much comes out of the tank, right? So how is that going to help us, right? Figure out how much is coming out of this tank. They want a mass, right? And in fluids, what's one way of finding a mass? We usually avoid finding mass. We use what instead? We use density, don't we? Right? So we use a density, and so to solve for that mass, I just take the density of my fluid and I multiply by the volume, right? Well, my fluid is water, so I know what its density is. It's 1,000 kilograms per cubic meter. So now what do I need? I need the volume. I know how fast water is flowing out. How do I find a volume? Bring your mind back to the equation of continuity. Equation of continuity was an area times a velocity equals an area times a velocity. We're not going to change the area yet. We'll do that in part C. Okay? But what we need to focus in on is that if you take an area and you multiply it by a velocity, what are your units? Covered this last week. It's a cubic meter per second. And what's a cubic meter? It's a volume. So if we can find the volume flow rate, cubic meters per second, and we know it flows for 2 hours, we should be able to find the total volume of liquid that comes out. So let's calculate this volume flow rate by doing an area times a speed. Our speed, square root of 2gh, did I calculate that? I did, 12.1 meters per second. So that's how fast it's going, okay? And then if we can calculate this volume flow rate, so the area, which is going to be pi r squared times, do it over here, pi r squared times our 12.1 meters per second, that will be meters cubed per second. So how do I just get the volume out of this? Yeah, if I multiply, I'm being messy here. I want to take this and I want to get meters cubed out of it, right? So I'm going to take my area times my volume and multiply it by my time in seconds. So that's going to be pi r squared times square root of 2gh, which is 12.1, times the amount of time. So it's 2 hours. How many seconds is that?
7,200 seconds.
How'd you do that?
Because 36.
Oh, 36 times 2. All right, yeah, okay. Numbers. What'd you say? 7,200 seconds. I got 3.32 times 10 to the 4 kilograms. So 33 metric tons. 33,200 kilograms. 33.2 metric tons of water. That flowed out. That's a lot. All right. And now we want to know what the gauge pressure of the water is flowing just behind the nozzle. Okay? So we've got to find out this again. Okay. What they're asking for is the pressure, the gauge pressure, right at that point behind the nozzle. Didn't talk about gauge pressure on the first day. Somebody asked me about it because I think the homework asks for it. Gauge pressure is the pressure compared to whatever the atmospheric pressure is around the thing that you're measuring. For example, what tire pressure should you have on your car? Just as an average, if we got normal tires. 35 to 40 pounds per square inch. Okay? You can always look for it in your car manual, but most of it was a manual. Nobody reads the manual anymore, right? So on the car, if you open your door, there's a white sticker somewhere. It's somewhere on the door frame or maybe even on the door itself. If they're really mean, it'll be on the underneath. You gotta look at it, right? But it's right in the door frame. Okay, if you look at that sticker, it's got a lot of information on it, but one of the pieces of information there is the recommended tire pressure for the vehicle, assuming stock tires, or the tires that the vehicle came with. If you've put specialized tires on your car for drifting or anything, it's a different story, right? Okay, but normal everyday, most tires 35 pounds per square inch, some closer to 40. You can also read it right off the sidewall of the tire. Okay, it can be kind of hard to read. If you make it wet, you can see the stuff a little bit better. Anyway, 35 pounds per square inch. That's what the pressure gauge reads. When the tire is flat, what does the gauge read? 0. But does that mean that there's a vacuum inside the tire? Like the pressure inside the tire is better than the pressure in outer space? No. What does it mean when the gauge reads 0? It's 14.7 pounds inside and it's 14.7 pounds outside the tire. And so a pressure gauge gives you the difference. It always gives you the net, not the absolute pressure. Absolute pressure inside a flat tire is atmospheric pressure. 35 pounds per square inch, gauge pressure. What would the actual pressure in that tire be? 49.7, whatever 14.7 times 30 plus 35 is. One of the fun things I like to do when I go to the doctor's office is what the nurses always take your blood pressure. Right? They take your temperature, your pulse rate, breathe rate, and they're just making sure you're alive. Anyway, when they give you the blood pressure, they give you 2 numbers, don't they? What's the normal average? 170?
70 over 100.
Oh boy, in America we just changed the goal line. Okay. 120 over 80, okay, is considered normal blood pressure. Now, this varies over gender, height, body weight, race, okay, for like what the actual sort of healthy target is. A lot of Asians will have like a 110/60, just sort of natural blood pressure. I knew this because I took a lot of Filipinos' blood pressures in my 2 years that I served as a missionary because we did medical stuff. But this is the standard in the United States. Just for it's a fairly, unlike human body temperature. This one's actually pretty good. Human body temperature. What's normal temperature for human body?
98.6.
If you're white male of European descent, okay, because that's where that number came from. It varies from individual to individual. Again, this one varies widely across race and gender. So yeah, what's the best way to know your normal body temperature? Check it. Take it for every day for a week at the same time of day, okay? And do it when you're not sick. Like Mr. Balogh, I live in Fresno, sick all the time, right? Okay, so take it, try do it when you're not sick. Take it every day at the same. Why same time? Okay, right? And if you're female, you know that during your period, your temperature can also change. Try to do it sometime sort of in the middle of your period, and take that for a week, and then you will have a baseline for what your normal body temperature is. My normal body temperature is 98.1 or something like that. Okay, it's actually a little bit depressed from the average. And so when I have like a 99.9 degree fever, I actually like am feverish, like I'm starting to not be able to concentrate and do all that kind of stuff. So again, it varies for different people. Medical advice from Mr. Balogh for the day. Where was I going with this? What units? I always ask the nurses. They say, it's 120 over 80. 120 over 80, what? Yeah, it's millimeters of mercury. Old pressure gauges, you would take a glass tube, you pull all the air out of it, get as good a vacuum as you could possibly get, and then you would take that vacuum tube and you would put it into a bowl of mercury, and then you would let the mercury get sucked up into the tube. Well, the mercury wasn't getting sucked into the tube, it was getting pushed into the tube from the atmospheric pressure on the surface of the mercury. So it would go up into the tube. And atmospheric pressure was measured literally in the height of a column of mercury. They used water barometers for a while, but you needed like a 10-meter tall tube. That was no good. Mercury is much more dense, so you only needed like a 1.5 meter tube, and you could measure changes in atmospheric pressure. It was measured in millimeters of mercury. In the weather report, when they say the atmospheric pressure is 29.9 inches of mercury is still the unit that they use for their pressure in meteorology. So that's where that came from. This is millimeters of mercury, and the top number means, what does that mean? It's systolic over diastolic. What's systolic pressure?
Top blood pressure.
That's the pressure that your heart is exerting, okay, through the constriction of the cuff on your arm. Right? They cut off the blood flow to your arm, okay? And then the computer or the nurse listens for when blood can first flow through the vein in your arm. Okay, they're listening usually right back here. Okay, and so they'll listen for that, and then the bottom one is kind of a weird one. This is like when they stop hearing the blood flowing. It's not really a minimum pressure that the heart exerts, because the minimum pressure the heart exerts is gauge pressure at 0, right? There's an instant there where the blood is not moving, and then the heart pushes again. But it's just a lower number. It's a little bit less, but the top number is the one. If somebody's got a blood pressure that's like 180, you got to start like looking at them, make sure they're not going to fall over. All right, that was a big tangent. What were we doing? Gauge pressure. Okay, gauge pressure of the water flowing out behind this nozzle. Okay, so if we're going to find that gauge pressure, I'm going to compare inside this nozzle now that the plug is out. I'm going to say 0.1 is inside and 0.2 is outside, right? So it's kind of squirting out, and there's water flowing in here. But I want to do this comparison right close to each other. So again, Bernoulli's equation. I'm kind of impressed that I was able to talk and write all the numbers down correctly. Did I get it? Yeah, I got it right. Amazing. Okay, So what's the height level between 1 and 2?
Same.
Here, it's the same. So we're going to go ahead and get rid of those. And again, pressure at point 1 is whatever it is. And pressure at point 2, 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. Pressure at point 2 is what? It's atmospheric pressure. The water has been let out, as it were. So since gauge pressure is absolute pressure minus atmospheric pressure, I can go ahead and just bring my atmospheric pressure over, and I'll have 1/2 rho is V2 squared minus V1 squared. And this thing right here, this is the gauge pressure. Because again, that gauge pressure is the difference between what the actual pressure is and atmospheric pressure. Which means I need these speeds, don't I? I need the speed inside that nozzle versus, I know the speed outside the nozzle, it was 12.1, wasn't it? Okay. So I need the speed inside the nozzle. The only thing I haven't used is the diameter, okay, of that outlet hose. It's 3.3 centimeters in the hose, and then it gets to the point where the water squirts out, and it comes down to, well, I kind of maybe drew this wrong before. Like it kind of cuts down here, right? Okay, so then the water squirts out through the nozzle. So the radius right here is 3.3, and this radius right here is the 1.1, right? Okay, so I can use equation of continuity down here. I know the speed outside, and I know the speed that it went through the 1.1 radius hole. So that means I can go ahead and find out what my V1 is. It's going to be A2 over A1 times V2. I think I did that. I found that V1 was equal to 1.35 meters per second. Check that. Should that speed be lowered? It's a bigger pipe going into a small nozzle. Yes, right? Because as the area goes down, it has to speed up, right? Okay. So that my number may not be right, but at least it's lower. If I'd gotten a higher number, I would have been like, what? What's going on? Okay, so I come back up here, I do 1/2 times 1,000 times V2, which was 12.1 squared minus 1.35 squared gets me gauge pressure 7.26 times 10 to the 4 pascals. And it's a positive pressure, which is a good thing. I'd expect there to be positive pressure down inside of the inside of that pipe. Because if there weren't, if there were negative pressure inside there, which way would the water flow? Back in, right? And I want the water to come. All right, so that was probably way too much to give you right after Thanksgiving. But nonetheless, patterns for working your way through these problems. And notice you had to bring to bear, right? The stuff we learned about pressure, right? At the beginning of chapter 40, we had mass, right? And the density, mass, volume thing, right? About the only thing we didn't do in any of these problems was Archimedes' principle, right? Archimedes' principle is a direct application of statics from chapter 12 with buoyant force in it. Okay. That marks the end of lecture in Physics 4A. I have nothing else to teach you. Bye. Bye. No. We got a lot to do, okay, before we get to the end. And we are you got to sprint. Got to sprint the entire way to the end, right? So let's begin that sprint by showing you what's going on here. All right. Let's go to homework. Assignments. Chapter 14. Should be due this Wednesday, is that right? All right, so there's some conceptual questions. I'll let you suffer through those. Okay. I looked and a lot of you had already started this, which was very, very good. Some of you haven't, so get started. The Trieste. Jacques Picard. Yes. Picard. Not the Enterprise one, but Picard's a famous name. Anyway. James Cameron did this too, didn't he? Didn't James Cameron dive to the bottom of the Marianas Trench?
I think he has the record now.
Yeah, I think he holds the record for deepest dive ever. At any rate, they wanted to know the pressure down at the bottom of the Marianas Trench. How do you find pressure when you're down deep in the water?
PO plus PG.
Yeah, rho GH.
Rho GH.
Right, rho GH, and then be sure to add that additional 1 atmosphere of pressure on the top, right? So 1.01 times 10 to the 5 pascals plus rho GH, where H is what? The depth. In this case, the depth is 10.9 kilometers. What do you got to do with the kilometers? There you go. Oh, Archimedes principle, right? I drew this picture in lecture, so go back and check the YouTube with that lecture. It's the principle of the hydraulic, right? Hydraulic being able to trade cross-sectional area for force and vice versa and all that kind of stuff. Only this one, I think, like, yeah, the small force F over here, and I'm not sure. Oh, they just want to balance it. So basically just find the force. Same on both sides. All right. Oh, the kids. Okay. I get a lot of questions about the kids on the raft. Okay. You can go through and you can solve this. So there's some things that they don't explain that are basically implied. Okay. So for the raft to be considered floating with the kids on it, okay, what's the limit where the raft is no longer holding up the kids? Like, what's the maximum the raft can provide in terms of buoyant force? Equal to what? Weight of the water displaced, but how much water can the raft displace? If the raft is floating on the surface of the water and half of it's above the water, how much volume is it displacing? Half of its volume. So now if it's 3/4 below the surface of the water, how much volume is it displacing? 3/4. So what's the maximum amount of water the raft can displace? Its volume. Right? They want to know how many logs are required. So we can find the volume of 1 log, right? And then the buoyant force that we need to support. We need to support what? What weight? What force do we need to support? The kids plus the logs themselves. Don't forget about that, right? And so this is like the balloon problem where we solve for the amount of helium. Only here, we're solving for the amount of logs. So if you can find out how much buoyant force 1 log provides, you can work out, you just want to put a little multiplier, like put a capital N in front of the buoyant force on the log, and solve for the number of logs that it takes to float these kids. You're going to get a number that's going to end in a decimal. Depends on the numbers that go into the problem, but usually it's like 3 point, let's say the number comes out to 3.2. Okay? The answer that you need to put in that box is the minimum number of logs it requires to float the kids. The answer is 4, not 3. Because if you round down, if your math tells you you need 3.2 logs, that's like the minimum amount so that the raft is just barely sunk, right? It's still floating, but it's below surface of water. The kids, the little toesies are getting wet, okay? But if you take out that 0.2 log, what's going to happen? It's going to sink, right? So the answer you have to put in would be 4. It's the total number of complete logs that you need in order to float the case. What if you got a number that was like 3.8? It's still 4, right? So it's not a rounding thing. You don't round. What you do is you realize, okay, I need a complete log. If I need 3.2 logs, that means I actually need 4 total logs in order to get this situation. So what I found in helping students in the past is they don't struggle really with being able to find out like the volume. Like I need 3.2 volumes of logs. They're like, what do I put in the box, right? Okay, you put in the integer number of logs, right?
It would have been nice if it would have said somewhere that it can't be a fraction, because I tried that.
Yeah, right. And again, they're not explaining really well that it can't be a fraction. It has to be a whole number. So
My hair out.
I'm sorry. Yeah, I should have warned you ahead of time. All right. Oh, fraction of the iceberg. So the one that gets it, somebody asked me this the other day and I completely messed this one up. I did it exactly right and then got the wrong answer because they want the fraction that is visible. And when you solve, right, I gave you the equation in class for how much like density, ratio of densities to ratio of volumes, I solved for the amount that was under the water. Right, I solved for the amount of fluid displaced or whatever. I was like, oh, well, 93% of the iceberg is loaded. The answer is 93. And it was like, red. Yeah. Like, I did this right. What's going on? They want the portion that's visible. I solved for the portion that's under the fluid. So what do? Subtract 1 minus 0.93 or whatever answer you got, right? Would be the amount that's above, where the polar bears and penguins live or whatever. Whoops. This looks familiar. They gave me cross-sectional areas. They've got a height, a D, a depth below the intake point, okay? And the pressure difference between the inlet and the outlet. Yeah, so this is a Bernoulli's equation problem. Instantly, just looking at the picture. Bernoulli's equation problem, right? It's got the pipe changing its radius. That means you're probably going to need the equation of continuity. Also, changing the size. What volume of water flows out during a 10-minute period? We know that trick now, don't we? Take cross-sectional area, multiply by the velocity. You've got a volume per time. And if they want to know 10 minutes, then I've got to do 36,000 seconds? No.
No, 600. It's 10 minutes, 60.
It's 30. It's 60 seconds in a minute,
Times 10.
not hours. I met a stranger this weekend, and they were asking me what I did. I'm a physicist. Like, oh, that's so cool. There's usually 2 things that happen when I tell people I'm a physicist. I usually try to avoid it. Right? Oh, what do you do? Oh, I'm a teacher. Oh, teaching's great or something. Blah, blah. What do you teach? I teach science. Oh, I love science. What science do you teach? I'm like, physics? There's 2 responses. Okay? First one is, oh. And then they change the subject or walk away, one of the 2. Usually there's some sort of trauma that I can see in their face from whatever they had to do in college. The other response is, oh, it's amazing. I've got this thing that I can prove to you that the second law of thermodynamics isn't true and free energy and the weirdo thing comes out, right? Right? So it's one of the 2 things. Anyway, they found out I was a physicist and they said, oh, it's so great. You can help me calculate the blah. I was like, stop. They were working on some project at their house, right? I was like, you never want a physicist to do any calculations. I can't explain the space-time curvature around your house. What you want is an engineer, right? That can tell you to actually help the house respond. I can help you in theory. I'm no engineer. We did it, right? We did this problem. frictional force between the pipe and the plug wall, right? Okay, the volume exits. We actually did more than this problem. Spring bound. So one of the things that is not also real clear in fluid physics is that whenever a physicist says we've weighed something in a fluid, you got to think of like, oh, they don't really have them anymore in the grocery stores. They had those balances where they had the pan underneath and you put the veggies or whatever in and the dial, right, as it hung down, it would, right? That's what we're talking about. This is not like we put a scale in a pool and have somebody stand on a scale. We don't do that. Okay, so it's hanging there, tension. We did this. This is the crown problem, but rather than finding the density of the object, we're finding the density of the liquid. That's all of your homework questions. Are there any specific questions on any of these? You want me to go into more detail, things you ran into as you were doing that you need help with? That's what half the people in the room go. Yeah. I think that's homework.
For number 5, I'm gonna just show you what I did for number 5. Because words cannot explain it, so. But I ended up getting it right.
You ended up getting it right, but you don't know how?
Yeah, like I had to use a different equation.
No? You use it correctly?
Oh, okay.
Yeah.
Even for the area.
Mm-hmm.
Area 2.
Mm-hmm. Are you asking why is it pi times diameter squared over 4? Okay. So, when they give you a diameter, you can either take that diameter and divide it in 2, right? An area is pi r squared, isn't it? And what's the diameter? It's you think you've answered the question I asked, but not the one I was thinking of. Diameter is twice the radius. Welcome back from Thanksgiving. So the radius is the diameter divided by 2, isn't it? This is what I was thinking. It just didn't come out right. And we've got to square that, right? So when we square, what do we get? Pi diameter squared over 4, right? That's the same as pi r squared. Just doing it in terms of the diameter. So whenever I get a diameter, if it's on the page, I'll actually cross it out, divide it by 2, and write the new number above it. So that from there on, I'm just using radius now. It's one of those triggers that I'm just like, as soon as I see a diameter, I kill it. Because I have been caught out so often by giving me diameter, and then I get into the problem, and by the time I'm ready to put the numbers in, I forget it's a diameter, I assume it's a radius, and then this is why you want an engineer. It's not this physicist. Any other questions? All right. Get rid of this. Is that still going? Okay. So for those of you that came in after the start of class, this is the instructions for turning in your quizzes, right? Important thing on the quiz. Make sure your name's on the sheets. Make sure the total number of points is at the top of the first page, okay? So not on every individual page, but like if you have 4 sheets and add up all the totals and then just put that total on the front. What I'll go through is I'll check and see if there's justification for all those points. But and I think the number is gonna be like 25 or 30. Did I change the number already? 30? Yeah. I went through. I only handed out like 120. So for section number, I mean like 8 a.m. and 11 a.m. I refer to internally 8 a.m. to section number 1 and 11 a.m. to section number 2. Right? There's section numbers. I don't know what they are. Okay. And no, it's not like oldest child, youngest child. I don't think they are. It's just 1 and 2. Just the okay. So anyway, I will see you on Wednesday for questions. Right? You ask me questions about ladders. Hopefully. We got to review all that statics and gravity. See you then.
Yeah, great.